We're good to go. Okay, couple things before I choke to death. All right, I asked you to skip number 3 as well, only because that one you probably can't figure out on your own. So I also asked you to skip number 3. We'll get to that today and during today's lesson. We are looking at a test sometime at either Friday of this week, depending. I know you guys have Honor Society stuff today, and then tomorrow is PSAT, so I might have to push it off for another day or so. But if I tell you the test is going to be Friday and I push it off till Tuesday, then that'll be a good thing. If I tell you it's going to be Tuesday and I decide to give it to you on Friday, then you're going to revolt. So I'm telling you it's on Friday, but it could possibly get pushed off depending on PSAT and Honor Society induction stuff. All right. We're finishing up the periodic table stuff this week. Here we go. Where do we find them? I want everyone to have in front of them a periodic table. If you don't have a periodic table in front of you, it's going to be much harder to do this. All right. Where do we find the most active metals? Bottom left. I love it. A man of conviction. Bottom left. What element on the bottom left is the most active and why? It likes to lose its valence electron. And it's losing it very quickly because that valence electron is really far away from the nucleus. Okay? So all of the elements that are in that first column, this first group right here, they all want to lose their electrons. But francium is going to lose them the fastest because that electron is furthest from the nucleus. Start to remember what the periodic table looks like so that it all starts to make sense. All right, where are the most active nonmetals located? Top right. So helium is in the top right. Is that the most active nonmetal? Why not? Because it's helium. That's very good. Give me a little more than that. They are close to the nucleus, but give me something else about helium. Yeah, why is helium not the most active nonmetal? Why is this element right here not the most active? You told me that it's top right is the most active nonmetal, so I assume it was helium. But why is helium not the most active? Kevin, put that phone away. It is a noble gas. And noble gases have full valence shells. So when I say top right, I am excluding that very last column. Okay? The noble gases don't count. Just an FYI, this is where the slope starts, okay? So the first couple weeks of school, now we just finished week 5, we kind of coasted through. From here on out, I'm going to be giving you a lot more information. So just putting it out there. As you go from left to right across the period, I asked you to skip this. So let's go to 4. As you travel down a group, the atomic size. How do we measure the size of an atom? Well, let's pretend this is a circle. Well, it is a circle. You can't see anything. That is a circle. How would you measure the radius of a circle? What's the radius? From the middle to the outermost edge. If you have an atom, in the middle you have a nucleus. So if I'm measuring the size of an atom, I am measuring from the nucleus, which is really small, to the outermost electron. That's going to be the radius of the atom. And that's how we measure the size of an atom. From the nucleus to the outermost electron. So now, knowing that information, if I go back to this question, it says, as you travel down a group, what happens to the atomic size? Let's take lithium, sodium, and potassium.
I said increases.
It does increase. Why does it increase? Circle increase. Kevin?
Because there are more like electron rings.
Perfect. Because there are more energy levels. Electron rings are energy levels. So the more energy levels you have, the bigger your radius is going to be. Okay? I asked you to skip number 3. We'll come back to that very shortly. Just wait. Okay? Now let's look at number 5 and 6. You needed to put your thinking caps on for number 5 and number 6. Let's go back to something I can write on. You got it? You understand what's going on? Okay. Let's take a positive ion. Does number 5 say a positive ion?
Negative.
Oh, negative ion. Okay, so let's do the negative one first. So here's a negative ion. Okay? Give me any element that you know will become a negative ion, and why does it become a negative ion? Fluorine. I like it. Fluorine as an atom looks like that. As an ion, it's going to become a -1. Why does it go from a fluorine atom to a fluorine ion? What is it trying to do? It's going to gain an electron to fill its valence shell. Okay? Everybody good with that? Okay. So here's the nucleus. In the first energy level, it has 2. In the second energy level, it's going to have 7. I'm going to put them on there. 1, 2, 1, 2, 3, 4, 5, 6, 7. That's the atom. Let me just copy it. And let's paste it over here. When it becomes an ion, it's going to gain an extra electron. There's my extra electron. Now it's an ion. Remember, when we draw an ion, we're going to put it in boxes, and we're going to put a -1 on the outside. Do you remember that? This is kind of like review here. What happens to the size of the atom / ion when I become a negative ion? I think you need to think hard about this. It does increase. Now, the real question is, why does it increase in size? Did I change the number of rings? No. So if we think of each one of those rings as like a bag, and I shove another thing into the bag, what's going to happen to the bag? It's going to expand. So this second ring out here just got another electron in it, didn't it? And when it gets that extra electron in it, each one of these electrons is negatively charged. And if you have 2 negatively charged substances next to each other, they're going to push away from each other. So it doesn't get bigger by a lot, but it gets bigger by a small itty-bitty amount because the negatives that you just shoved into that shell are going to repel each other just a little tiny bit more. Does that make sense? So if I go back to the question, it says a negative ion is larger, this is a big pen I have here, than its parent atom, and we're going to write next to it because of electron repulsion. Now, electron repulsion is just a fancy way of saying you've got 2 electrons, they're both negative, they're going to push apart away from each other, they're going to try to get as far away from each other as possible, so therefore it's going to just go pop, just a little tiny itty-bitty bit. Okay, that takes care of 5. Now, let's do the positive one. If you have a positive ion, is it going to be larger or smaller than its parent? It's going to be smaller. Makes sense because we just said larger for the other one. Now let's think about why it's going to be smaller. Okay, so let's get an element that becomes a positive ion. I'll take sodium because it's easy to draw. So here's sodium atom. Here's sodium ion. The atom looks like this. You've got 1, 2, 3 rings. Those are perfectly round circles. I don't know how that happened. 1, 2, then I have 8. Does everybody know where these dots are coming from? Okay. When it becomes a sodium ion, come on, paste. Okay. what happens to it? It loses an electron. So when it loses an electron, it's going to lose this outer ring. Why did it become smaller? It lost an energy level. It lost a ring. That's why it became smaller. Please, I beg of you, do not say it got smaller because it lost an electron. Even though that is true, that's not why it got smaller. It got smaller because it lost an energy level. Why did the fluorine get bigger? Because of electron repulsion, not because it got more electrons. The electron is too small to make a difference. All right, so now this sodium over here is a +1. I'm just going to put it in brackets and put a +1 on it. And so therefore you have a sodium +1 ion. Good? All right. So that takes care of number 5 and 6. 7, 8, 9, 10 is today's lesson, so we'll get to that in a little bit. Number 11. What are group 1 called? Alkali metals. Alkali metals. They are highly reactive. They're the most reactive on the periodic table. You will never walk down the street and find one laying on the ground. It will always be part of a compound. Group 2 are called the alkali earth metals. Groups 3 through 12 are called the transition metals. Okay. As you go from left to right across the periodic table, so if I'm looking at a periodic table and I'm going from lithium to fluorine or neon, left to right, the elements go from being what to being what? Metal to non-metal. That means the metallic character, that's the word they're going to use, is going to decrease as you go from left to right. It does not ask this in this worksheet, but as you go from top to bottom, what happens to the metallic character? As you go from top to bottom, do you get more metallic or less metallic? More metallic. Does? Where? Oh, yeah. So we can answer number 22. Becomes more metallic. All right. Group 17 are called the halogens, also known as salt formers. And the most active element in group 17 is going to be fluorine. Group 18 are called the noble gases. All right, 17, we're never going to do 17, 18, we skipped that. Elements within a group have similar numbers of valence electrons. I want you to write this down. I want you to write down they have similar chemical properties. The reason I want you to write that down is because they love to ask that question. If you are asked for two elements that have similar chemical properties, they're going to have the same number of valence electrons. They're going to be in the same group. All right, elements across a series. I changed the word to period because that's what we call them in Regents chemistry, periods. What do they have similar numbers of? Energy levels. See how smart you guys are? Good job. All right. A colored ion generally indicates that you have a transition metal. This is not ground and excited state electron configuration I'm talking about. This is when you have a salt that's formed, like iron, regular old iron. If you look at iron, it looks like a metal. It's shiny, it's silver colored, whatever. But as soon as it becomes an iron ion, that means it becomes a salt, it's going to be that reddish orange color. Or copper is going to be the green color. Or cobalt is going to be blue color. Or manganese, my personal favorite, is purple. Okay, I like the manganese. It's pretty cool. All right, a majority of elements on the periodic table are metals. Elements in the periodic table are arranged according to their atomic number. That's periodic law. An element with both metal and non-metal properties is called a metalloid. Yippee skippy. Any questions on that stuff for now? I know we skipped a few. We'll come back to them. All right, turn the paper over. There's letters up here. We just got to match them up. So which one's the alkali metal? C. How come it's not I? Hydrogen it's a gas, but it's also not a metal. Okay? All right. An alkali earth metal. That one's easy. F. An inactive gas. A. A, B, C. Oh, A. An active an inactive gas. An active non-metal. Oh, I read it wrong. All right, an active non-metal. I'm going to go with H. A semi-metal. B. All right, number 6. An inner transition element. Okay. All right, E. I would take E because you don't know any better, but it's really D, and I'll tell you why. Because remember down here we have lanthanide and actinide series that fit right in here? They're inside the transition metals. That's what that means, inner transition metal. So whatever you put here, you could put an E, or you could put, what's the other one? D. D is really the answer, but if you put a transition metal with E, that's fine. All right, the most common oxidation number or state is -2. Where do we find -2 oxidation numbers? I like G. What element is G? It's oxygen. Oxygen, start to commit that to memory. Oxygen is almost always going to be a -2. All right, a metal with more than one oxidation number. E. I think that's iron or copper. Depend. Okay. Cobalt? Okay, and it has more than one. It should have +2, +3, right? Okay. Metal with an oxidation number of +3. J. And has oxidation numbers of both +1 and -1. I. That's hydrogen. Hydrogen is, you remember, hydrogen can't make up its mind. Is it wants to act like a metal, wants to act like a non-metal. It doesn't know if it wants to give away its electron or grab another one. You know, hydrogen is one of those funky ones. All right, here we go. New stuff. Maybe, if I can get to a new page. You all right, Kevin?
How do you oxidation levels?
They're the same as the charge. So they're right here. If you look, see how it says oxidation numbers, select oxidation numbers? Okay. That's just these charges. Okay. It's just a fancy way of saying charges. Okay? All right. So on this little page, for some reason, when I made this, I didn't get rid of the placeholders, so don't worry about what's going on down here. There are something called periodic trends. And we've kind of already talked about reactivity. You know, because I talked about it last week, where the most reactive metal and where the most reactive non-metal are. What is a trend? What's a trend? Okay, common occurrence. Something that happens and then it starts to grow, and then like you watch a trending thing on TikTok, right? I decided I'm going to start my own trend. You ready for it? No. I'm going to wear a clown nose to school. And then Willow's going to think I'm the coolest person ever. So she's going to go out and she's going to get a clown nose. And then Olivia says, oh man, I just think you guys are the bomb.com. Is that even a thing anymore? And, no? And she goes out and she gets clown noses. And then next thing you know, everybody in the class is wearing clown noses. And then Mr. Esposito's class next door, they're like, wait a minute, how come we don't have clown noses? And it starts to grow. That's a trend. right? A trend means it's going in a certain direction. It's trending in that direction. Water bottles. Water bottles were never a thing. And then all of a sudden somebody said, oh, don't I look cool carrying a water bottle around? And then everybody else is like, oh, I should be cool like them and carry a water bottle around. That's a trend. Okay? Somebody wearing a cool baseball hat. And everybody else wants the same brand of baseball hat. That's a trend. Okay? So on the periodic table, we have these trends.
You meant to, did you highlight or cross out?
I crossed them out because, like I said, I don't know. I never really. It was a template, and I never got rid of this. Okay, so let's just pretend this doesn't exist down here. All right. So if we look at reactivity, which we've already done, we kind of already know what the trend is going to look like. Right? What's the trend in this particular group for reactivity? In other words, what is it doing as I go from top to bottom? Is it becoming more reactive or less reactive? More. That's the trend. As I go down the group, I am getting more and more reactive. If I look over here from fluorine to UUS, what is the trend for the nonmetals? I am getting less reactive because fluorine is the most active nonmetal. Okay? So there are trends that we're going to see on the periodic table that are happening over and over again. The first one we're going to look at is atomic radius. Now, with radius, I already told you today how you measure the radius. It's going to go from the nucleus, that's all I drew, a little dot, to the outermost ring. Okay? So let's say, actually, let's get rid of this. Okay? Let's say we have hydrogen. Hydrogen's right here. Okay? It has one ring. And then we get lithium. Lithium also has a nucleus, but now it has two rings. Then we get sodium. Hey, that kind of looks like an eyeball. 1, 2, 3. What's the trend? Uh-oh, where'd it go? I hate when it does that, because now I don't know where the heck it went. Here it is. What's the trend as I go down the group?
Scanning electron levels.
It is, but what's the trend? Is it getting bigger or smaller? It is getting bigger. So the trend is, it is getting bigger. Why? Because you are putting extra energy levels. Okay? Now, here's the thing. With the trends, especially the... Okay, so something's happening here. I don't have free Wi-Fi. Oh. They don't even let us have Wi-Fi. Okay? So this is the one I'm looking at right now. Okay? Atomic radius. You don't need to memorize the trend. You need to flip your reference tables to table S, as in Sally sells seashells by the seashore. It's the next one after the periodic table. And now I'm going to jump up here. And we are going to look. In the very last column, come on. In the very last column, right here, it says atomic radius. How convenient. Okay? And if I look at lithium, this is where I need you, because you have a reference table in front of you, right? If I look at lithium, what is its atomic radius? 130. What's sodium's atomic radius? 160. Potassium? What? 200? All right. What about rubidium? Number 37. 250,
15.
215. Cesium, 238, and this is like francium, 87, 242. What happened to the radius as you went down the group? It increased. We already knew that because it is increasing because you're adding more energy levels. Did you have to memorize it? No. Do you need to know where to look for it? Heck yeah. Okay? All right. Now, back to that question number 3 that I asked you to skip before. I'm going to look at lithium all the way over to fluorine. I'm going to skip neon for now, but you could go to neon if you want. But I'm going to go from lithium to fluorine. We know lithium's radius is 130. What's beryllium? What is it?
84.
84.
99.
99. Okay. And boron? 84. And carbon? 75. And nitrogen? 71. And oxygen? 64. And fluorine? 60. Okay. What happened to the radius as I went across a period? It decreased. All right. Now, I want you to think about why it decreased. Okay? You need to think about the entire atom and what is happening as I go from left to right. Let's see if somebody can come up with it. From left to right, it's going to do this. Okay, you can get that right on table S. Those numbers that I wrote in green up there. You see them? Okay. Did I change the number of rings for any of those elements going across? No. So it didn't lose a ring. So why is it getting smaller?
As you go right, more electrons are in each ring.
You are getting more electrons, but what else are you getting more of? Who said that? Izzy. You're getting more protons, right? And the protons, if you think of protons as like people standing in the center and pulling, they're pulling on those electrons. And they're pulling on 2 rings. They're pulling on 2 rings whether you're here, and they're pulling on 2 rings whether you're here. This lithium only has 3 people standing in its nucleus pulling on those 2 rings. But fluorine has 9 people standing in its nucleus pulling on those 2 rings. And so therefore, fluorine has the rings being pulled closer to the nucleus because it has a stronger nuclear charge. Mind blown? Okay. We did not change the number of rings, but we did change how strongly we are pulling on those rings of electrons. Okay. Now once again, you do not need to memorize the trend for radius across a period. What you do need to know is where to look for the trend. And the trend is going to be on table S. Now here, everybody eyeball up here on me because I'm cute and you have to listen to this. When you're asked for a trend, Trinity, you ready? I only want you to look at the first one and the last one. I do not want you to look at what's happening in between. Because every once in a while, you're going to get one that goes boop. That's not going to follow the trend. So when you look at the trend, you look at the first one, you look at the last one, and you tell me, does it go up or does it go down? Okay? Because inevitably, there's going to be me with my big red clown nose, and all of you guys are going to be out there with your big red clown noses. And then Michelle's like, I don't want a red clown nose. I want a green clown nose. She's going to be the one that's different. So in here, there's going to be somebody who doesn't follow the trend exactly. So when you are looking at trends, I only want you to look at the first and the last. And then you'll get it right every single time. Do not try to look at all of them. When we do the lab, you're going to graph all of them. But you are not going to look at, when you look at the trend, you're going to look at the first one and the last one. Has everybody got that? Okay. All right, so that's atomic radius. As you go down, you increase in atomic radius. As you go across, you decrease in atomic radius. Why do you increase in atomic radius as you go down? More, not more electrons, more energy levels. Why do you decrease in radius as you go across? You gain protons. You get more nuclear charge. So therefore you're pulling on those rings. You guys are rattling around. Am I running out of time?
Yep. You have 30 seconds.
I have 30 seconds. All right, let me stop this.